Hi guys, so this video is the test corrections video. I'm basically just going to walk you through the steps of your homework. Skipping is enabled on this video so you can skip over the questions you got right, but I do want to give the instructions one more time because it was jumbled at the end of class. Right now, make sure that you have your Unit 2 test, which I handed back, and your test corrections sheet. You may also want to have one of those boxed pieces of paper. Looks like this, although yours is blank. Once you've got those out, here's the instructions. You are writing on this piece of paper. You're going to copy the test question here. I know this sounds tedious, but calculus is a language, and just like in a language class, you're going to have to write sentences and copy sentences, stuff like that. This is part of the work. It's not just the math that you're accountable. These words mean things and you need to write them here. You're then going to put the correct work, which I will explain in this video, and then you're going to do the example that I give you in this video. And then you're going to recreate your own example, which should look and sound just like these two. This example you're going to work out. The point is that you're focusing your efforts on the math that you didn't understand the first time around so that when the when the midterm comes, you do understand it. While you work the problem out here, you're also going to copy this over using nice handwriting and pen into the box sheet of paper. So you'll create a sample question like this. Please put the C symbol with an X through it to indicate that it's a non-calculator problem, as will I, so you can see how that works. When you come back to class, you'll turn this piece of paper into me. Please make sure your handwriting is easy to read and that you write in pen, because I'm then going to photocopy and make flashcards for everybody else so that you start to build up like a question bank of questions to study for the midterm. All right, got that? Let's get started. We'll start with question 1 from the test, and I'm going to zoom in here. If you remember, this first question was talking about f of x equals 1 over x squared plus 3. The correct answer was E, which you may or may not already see. At this point, if you have this question right, skip ahead to the first question that you got wrong. If you got this question wrong, let me explain my thinking process. So basically, they're giving me 3 statements, and I'm wondering which one is true. My first step was to think about what the domain of the function would be. I know that the rule for domain, there are basically 2 rules. I'm not allowed to have a 0 on the bottom, and I'm not allowed to have a negative number inside of a square root. Well, there's no square root here, so the only possible restriction, as in the only possible problem, would be if there was a 0 on the bottom. In order to get 0 on the bottom, x squared would have to equal negative 3, because then when you add it to positive 3, it equals 0. But x squared can't equal negative 3, because x squared has to be positive. It's just a squared number, which means that there is no way the bottom of this function could equal 0, which means that there are no domain restrictions, which means that I can plug any number I want, which means that the first one is correct. The domain is all real numbers, because x squared is always positive. Now, even function and symmetric with respect to the y-axis, those mean the same thing. So if one's true, then the other has to be true. And the way that I checked even function was I plugged a negative x into the rule for the function, and then I used algebra to simplify. When I squared a negative x, it became a positive x squared. And when I see that I plug in a negative x and simplify, I got the same function back, the original function back. In other words, f of negative x equals f of x. That's the definition of an even function. So I know that both 2 and 3 also have to be true. Hopefully you get this now. Pause the video if you need to continue to write this down. Otherwise, you should be ready to go. Here's the problem that you're going to complete. Notice how it's almost exactly the same as the one that you just did. Great. So you saw the answer in Edpuzzle, but here's my explanation for that first question that you just worked out. Take a moment to read what I wrote. So hopefully this makes sense. Notice that there were kind of 2 things I had to do. First, I thought about the domain, and I found that there was a problem when x equals 0, so 0 is not in the domain. And then I used that same strategy by plugging in negative x. This is the only tricky part right here. Sine of negative x is the same thing as negative sine of x, and the reason I'm allowed to pull that out in front is because sine's an odd function. So actually to do this step algebraically, I had to think about the graph of sine. Odd means that it's rotated around the origin. In other words, it's kind of flipped 180 degrees. Because of that, if I take sine of a negative number, the answer is just the negative version of the positive number. You can kind of visualize it here graphically like that, if that helps. From there, you know that the negative just disappears because we square it. Everything else should make sense. Pause the video here, and you're going to create your own. Remember, it should look exactly like this, and you can put the little no calculator symbol. Choose your own function, make 3 statements up. Great, so you should be used to the process now. I'm going to start to go a little quicker. Here's number 2. My rationale for answering B for number 2, we're taking the limit at positive infinity. I noticed, first of all, that I can't plug in positive infinity on the top and the bottom because both seem to be going to infinity. But I know that I'm not allowed to just write infinity over infinity. That doesn't mean anything. So what I thought about was like an end behavior model. I knew that the top function was kind of like the function 2x once we get to really large x values, and the bottom function would behave a little bit like the square root of 4x. The square root's really important. And then I did something kind of subtle, which is I realized that the power on the top is kind of like x to the first power. And the exponent on the bottom is kind of like x to the 1/2. And obviously there are coefficients, but ultimately the coefficients don't really matter. Because the exponent is larger on the top and we are going to infinity, the top is getting bigger more quickly than the bottom. In other words, what we have here is going to be a situation where we have infinity over 1, which is why I got an answer of infinity. Now, this isn't a numerical way of working it out. This is just my intuition. But it's a multiple choice test. There's no problem in using your intuition. Use the same idea to work this one out. Great, here's my answer key for this question. Notice that I did it 2 different ways. This is the kind of intuition. The intuition here is that the power on the top is smaller than the power on the bottom. So since we're going to infinity, this only works at infinity, the end behavior model that I should think about is like 1 over infinity, which would be 0, and that's the answer it shows. Technically, what you could do to see this is you could divide both the top and the bottom by the largest power of the bottom. So I'm dividing by x. And then do a couple algebraic steps to get an actual technical answer of 0. This is what you would do if you were doing this on a free response section. You can pause if you want to look at it more. Otherwise, we'll move on. Question number 3 was a trig question. My strategy for trig questions is always to try and get a sine over x, or in this case, sine of 2x over 2x. Because if you can rearrange something like that, you know that the limit as we go to 0 of a term that looks like this, or even if sine were on top and 2x were on the bottom, that would equal 1. So kind of thinking about our problem-solving seminars, where we're headed, the second you see trig, that should be your instinct, to try and like break things apart and rewrite them to get something that looks like this. You can pause if you want to look through any of my steps. I don't think anything here should be confusing to you. This is just another way to write tangent, and I broke this up into 2 fractions with multiplication, so the 1 over sine of 2x I just wrote over here. At this stage, I multiplied times 3x and divided by 3x. I added those in because I knew that I wanted sine of 3x over 3x. And if you think about working backwards, you should see that the 3x and the 3x will cancel out, which is why this equals the same thing as this. Same thing with the 2x and the 2x over here. Great. Here's your problem. Same idea. And the answer, here's how I worked this one out. Again, my strategy was to like rewrite tangent first. I know that right now there's a problem because plugging in 0 would make sign 0 on the bottom of the fraction. I split 6 into 3 times 2. You may not have seen right away that you should do that, so maybe you wait till later, but it's not a problem. The big step here was keep, change, flip, where sine over cosine on the bottom of the fraction turned into cosine over sine with a multiplication. And at this stage, you should start to see, oh, what I really want is sine of 2x on the bottom and 2x, because the limit as x approaches 0 of this term equals 1. And then the limit of x as x approaches 0 of 3, and the limit as x approaches 0 of cosine makes the rest a no-brainer. Remember that after each of these problems, you should be creating your own. So this was the original problem that you are trying to duplicate. Make sure it looks just like this on your square page. All right, question 4. Question 4 was really just about knowing your function families. So I would have thought about sketching the graphs of each of these. I know that the natural log has a vertical asymptote, not a horizontal asymptote. And whenever you see y equals, this is telling you the name of a horizontal asymptote. So I immediately ruled that out. I also know that this is exponential decay, and the asymptote's at 0, so I can rule that one out. And I know that sine is oscillating, going up and down, so it doesn't have an asymptote. Out of these two, now it's a little bit trickier to tell. Remember that the meaning of an asymptote means that the limit as x approaches infinity of the function equals 1. An asymptote is an end behavior. So if I think about taking the limit of each of these functions as x goes to infinity, this function is going to go to infinity as well, because the exponent power on top is larger than the exponent power on the bottom. So this one doesn't have an asymptote. This one, however, the exponent power on the top and the bottom are the same. An end behavior model would actually be x over x, in other words 1. This one is going to have a horizontal asymptote. You could work out the limit if you feel unconvinced, but just recognizing the leading power on top and bottom usually is enough for most people. Here's one for you. Great, and here's the answers for this one. Notice how I sketched out 3 of them, and then I actually had to think about the limit for D. But B was just a shift up right there from your exponential function if you see it. Great, let's move on to number 5. Number 5 is all about remembering your algebra 2. How fun. And to work this out, first of all, I recognize it's a piecewise function. I actually think that maybe the easiest thing for you to do would be to kind of just do a rough sketch of the graph. We know that the graph is shifting functions at 7, so let's call this 7 and make the little dotted line. On the right side of 7, it's a linear function. So if you plug in 7 right here, 2 times 7 is 14, minus 3 is 11. So this function is going to start at 11 as your y value. It's going to be an open circle because there's no line, and it's going to be a positive slope, so it's going to go up like that. Algebraically, if you wanted to write down that idea, this right here is saying the limit as we come from the right is 11, and that's just from that function. From the left, you end up getting 9, and that's just if you plug 7 into this expression right here. And you may not necessarily know what the function looks like, but you can just put the dot here at 9, which is going to help you see right away that there's going to be a jump. We don't know what this function looks like on the left. Doesn't really matter. You can't use your calculator, so do this in your head. There's going to be a jump, which is a non-removable discontinuity. So I know that 3 is true. Now, 1 is asking me what happens at 5. Well, positive 5, which is going to be in here, belongs in the region of the first function. I notice right away that I can't plug it in because the bottom is going to give me a 0. That means it's either a whole or asymptote. I use the algebra 2 strategy of factoring, and I remember that when there's the same factor on the top and the bottom, it causes a whole. The other thing you could do is imagine plugging in numbers close to 5 and checking the limit on either side. If the limit on either side is the same, that's how you know it's removable. If the limit on either side is different, it would be non-removable. But because it's a whole, we do consider that removable, which is why 1 is also true. Go ahead and try this one for you. Great, and here's the work that I did to answer this question.